So this is where we find the superconductivity in these methods. And when we wrote this, we left open how does it go to half filling. There's clearly no superconductivity at half filling because of the Mott gap, but it can go in a first order way or just very quickly. And these are more recent calculations by the student of Giovanni. So for all these U's, you can see the superconducting transition temperature is along this curve, the red points, and the color plot is the magnitude of the order parameter. So the order parameter is maximum, not at the same place as the superconducting order parameter, and that's most easily seen on these plots. Well, let's look at this one, for example, for U equals 12. You see there's a superconducting dome, and this is the maximum of the order parameter. So this maximum of the order parameter seems to track this 10%, but it goes to very low doping. And if we look at a case where we see the Widom line and the first order transition, so this would be U equals 7. This is the TC. The black spot is the maximum of the order parameter, and the dashed line is the Widom line. So the maximum does not coincide with the Widom line, but it seems to have some relation. Yes.
So is it a general feature that around, so the dome is not very symmetric around?
Yeah, that's one qualitative feature, that it is not very symmetrical. Pardon me?
Yeah, so it depends on...
For this cluster, yeah. And no, but for you, I will show in a minute, but for your cluster also. Yes. And experimentally, it also falls very quickly, but it could be due to competition with antiferromagnetism. So the TC, why is TC sort of sticking around? We believe that it's because in this small cluster, as soon as you form a pair, then you will get the mean field transition. So here I will look like somebody who is not very critical, and I just put a lot of experimental results for you to look at peacefully after this talk. But there are many, for example, there's this statement about STM measurement that said that our measurements demonstrate that the nodal gap does not change with reduced doping. The pairing strength does not get weaker or stronger as the Mott insulators approach, rather it saturates. Then there are these infrared response experiments that have an onset, what they call a T onset, which looks like a local pair formation. In our PES, there's this green line. In magnetoresistance, there's this T2 line. There is the giant proximity effect, where you have superconductors with very different TCs, and you sort of go across this very large underdope region. So, well, what is the true TC? In a bigger cluster, it could come from quantum and classical phase fluctuations, from fluctuation of the magnitude, from competing order, or Henri has argued that it can come from disorder. And these are the bigger cluster calculations that Olivier participated in, and you see that it's also very asymmetrical. And but here it ends. It does end before you get to half filling. The position of the maximum is very similar to ours. It's around 4%. Oh, I'm sorry. I should have told. Yeah, you should look at the black curve. The red curve is a function of U over U Mott. It's something else. So you just look at the black curve. Now, I don't have time to go in details, just to say that same question that Catherine asked about the antiferromagnet. Is there a first order Mott transition in the antiferromagnetic state? The answer was no. And here in the superconducting state, there's no first order transition also. So in summary, below the dome in this approach, what is there is a first order transition, not a quantum critical point, although, as I said, this critical point goes down very quickly with interaction strength. So does it eventually become a quantum critical point? I don't know. The maximum is near the Widom line. T star is different from this sort of mean field TC. So definitely the pseudo gap is different from local pairs, and this was also demonstrated in experiments by Henri Aloul on the effect of disorder that is completely different on supraconductivity and on the pseudo gap. What is the actual TC? Well, I just discussed this. Yes.
What is this dotted line? Within the
Okay, so this is technical. The first time we did this calculation, we did not have the algorithm was not ergodic. We used what was in the literature, and what was in the literature was not ergodic. So we had to. There's a there's a year effort here in doing this.
Quick comment about the previous slide. So this critical point, if you once again consider coupling to the lattice, actually it's a misnomer because there is no criticality associated with it.
Because you're saying that the lattice will couple to this and will make it disappear.
And because it's a solid and there are finite shear modes, you can show that there is no criticality.
I thought it would change the universality class and make it more mean field when you couple to the lattice.
Yeah, so if there is no criticality, it's just mean field.
Can I ask a question to the guy who asked the question? Why you say there is no criticality?
Because the fluctuations
Are you talking zero temperature or are you talking about the critical endpoint?
I'm talking about the endpoint. So whether the endpoint is at finite temperature or zero temperature, I think the statement is the same. So it's a paper by Marcus Garst, who is the first author. But the physics is that because you're in a solid and you always have shear modes, and so you can show that the equivalent of the critical fluctuations always have a finite value.
Well, certainly experimentally, around the critical endpoint of organics or V2O3, everything scales. There is exactly the scaling that is expected from Ising model at liquid gas phase transition. Very mean field, in fact. So this is something maybe we should discuss.
Okay, so
For T equals 0, this is finite.
No, I'm talking about the critical endpoint at finite temperature. It's an Ising thing. It's been demonstrated experimentally. I think.
Yes. There's a paper that just came out in PRL actually about the organics. Yes.
Yes, on V2O3, in which all the scaling functions of the liquid gas stream have been revealed experimentally in the transition.
Yeah, the paper I know is that when you couple the phonons, it was a paper by David Nelson and somebody else, was that it becomes more mean field, but not that it gets rid of the.
well, mean field in what sense?
It's by Jawad, 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 something else, yes.
Well, I can show you later.
Maybe we should discuss this.
Or at least experimentally it is seen, okay? So superconductivity, so you're all familiar with the fact that there's an attraction mechanism in the standard BCS theory and that it is retarded. So the electrons don't get at the same place at the same time. And the effective attraction is between a pair here and a pair there. So if you look at the ingredients for superconductivity, there's Cooper pair formation and phase coherence. So if you just look at the potential energy, for example, you see that if U is negative, attractive, then you can gain a lot of potential energy by having the same phase for destroying a pair and creating a pair. Because if the phase depends on P, then they will be scrambled and you will not get as much as you could have if they had the same phase. So in BCS is basically the mean field theory of this, at least this potential, the kinetic plus potential energy. And because this does not conserve particle number, then you should have wherever you put the pair, whichever value of P or P prime, it has the same phase. And this phase rigidity is called the superfluid stiffness. And the zero temperature limit, for example, in this paper by Gould and Millis, has this. So this is the superfluid stiffness as a function of doping, and you see it has this very characteristic sharp drop that we find also in our calculations. So this is for U equals 9 at very low temperature, and you see the order parameter and the superfluid stiffness. There are two lines here because there are some uncertainties in the calculations that I will discuss in the last lecture, but that's sort of an estimate of the error bar if you want, and then it falls very quickly. If you look experimentally, you see you have 10%, 15%, 20% doping, 22, 24, and then it goes to 0. So this is sort of going up and down suddenly. If you increase the temperature, you get a dome shape like for both the order parameter and the superfluid stiffness. And if you look at the corresponding temperature, you see you get 10, 15, 20, 24. Now it's indeed more like a dome. Again, I don't want to claim that it's quantitative, but qualitatively it is okay. Now, if you compare with the number of carriers, you remember this plot here that shows that the number of levels of states near the Fermi level is proportional to doping. And that was in the Hubbard model. So here, instead of, like in BCS, having the full electron count, or a part of it as the value of entering the superfluid stiffness, instead we have just measured compared with half filling. And okay, these are more detailed just to show that we did all the values of U. Now, what about the condensation energy? So these are old papers by the group of Jarrell that show here that the kinetic energy of the normal state, so this is the kinetic energy of the normal state in black here, as a function of temperature for some very small doping, is larger than the kinetic energy of the superconducting state in the open symbols. And if you look at the potential energy, it's the other way around. So in ordinary BCS, it's potential energy that you gain, kinetic that you lose. Here in the underdope regime, it's the other way around. And if you look at more recent calculations of Gould and Millis, I won't go through the details, but it's the same results. So in this region, in the overdope region, the gain in the condensation energy comes from potential energy. In the underdope region, it comes from kinetic energy. So what is the glue in this problem? Let's ask the question more generally about superconductivity. So there's a cartoon BCS weak coupling, weak correlation picture that is as follows, and it came out from Vic Emery and Claude Bourbonnais, who was a student in Orsay at the time. So this was the first paper who mentioned that you could replace the phonons by antiferromagnetic fluctuations. So there was then a paper by Scalapino, and in some sense it's extensions of very old idea of Kohn and Luttinger. So suppose that U is attractive here. So it means it's negative, so you get rid of the minus sign. Now everything else here, the energy here in 1 minus twice the Fermi function, the energy is square root of epsilon square plus delta square, so all of this is positive here. So if U is negative, you can take delta to be a constant, and you get a solution to the gap equation. If U is repulsive, you can still get around in this way. Suppose that you take delta here, and suppose it's positive. Then if P minus P prime is peaked around this direction, which would be the case for antiferromagnetic scattering of antiferromagnetic wave, then you see that it's P prime here in this region that's important. And since it's negative, you get rid of this negative sign, and you can still get a solution. There were detailed calculations more than 20 years ago by a group of Scalapino, where you can reframe this in terms of you can compute the TC from some eigenvalue equation, and lambda equals 1 correspond to TC. And the most recent calculation that's in 2011 by Jarrell's group show that for 16 side clusters that indeed you want to have an eigenvalue. That's the red curve that is going to 1. But then when they look at u equals 8, this sort of glue approximation does not work very well. So what happens for large value of u? Well, this goes back to the very beginning of ITC, where Anderson proposed that if you look at the super exchange interaction, then you can factor this a la BCS, and you will get some attraction here, minus J times D. And this was done, actually, it is this paper by Cotillard and Liu with slate boson that found D wave first. Anderson credits this to Pitaevsky and Bruckner in the theory of nuclear matter, but I could never find this reference. So how do you get this negative sign? In a cartoon picture, again, if you take just the SZ component, you see you have n up minus n down, n up minus n down. You take the n up times n down here. So in terms of creation annihilation operators, and just by shifting one of the fermions by 2 across 2 others, you see that you get this pair, these pairing channel here, and it has a negative sign. So now if you add charge instead of spin, so I get a plus here, you see that I have a repulsion. It will not be binding in the case of charge, but it is in the case of spin. So the question was raised by Anderson in 2007, well, a long time ago, but then there was this cartoon that appeared in Science, it's sort of a magazine, so they need cartoons. And the statement was that there's a mammoth and an elephant in the refrigerator. So this is U and this is J. And why do we need a mouse? So the mouse is the spin waves. And well, the answer of Scalapino is that, well, in ordinary superconductivity, there's retardation. So the statement of Anderson is that we just bind in a mean field way with J and forget about retardation. And then Scalapino says, well, there's retardation. So you can read these two E letters here, and you see they don't spare their words here in this debate. So if you go back to the electron phonon case, so you see that this is the anomalous part of the self-energy, the one that enters the Gorkov function. And this is the phonon spectrum. So you see that the 2 peaks in the phonon spectrum come here. And in fact, you can see harmonics that are predicted by BCS theory. So, or Eli-Ashberg theory, I'm sorry. So this gave people confidence that this was the right theory of superconductivity. Now what happens in our case? So these are, again, 2x2 cluster for exact diagonalizations. And if you look at the anomalous part of the self-energy for different dopings, this is very close to half filling and this is more dope. You see again these 2 peaks. Now if you just plot the imaginary part of the spin correlation function, local spin correlation, then you see also these 2 peaks. And you see that they follow, I mean, I just take the magenta points here and put the maximum as the magenta. And you see that they follow what's happening in the spin. And this is an experimental paper where they looked at the magnitude of this low-frequency peak as a function of Tc, and they see that this peak goes to 0 with Tc, as it does here, because the red curves are for the normal state. So more specifically, the shape of this spectrum, this spin fluctuation spectrum here with the 2 bumps, is reproduced here in red. And if you look now in the normal state, you see that this higher frequency peak, this is the black curve, is shifted to the right, just as it is in these calculations. So again, there's this qualitative agreement. Yes, Antoine?
Can you explain the physical origin of the second peak? Why do we have two peaks?
In the ordinary superconductors, it's easy to understand because there's longitudinal and transverse phonons. Here, I don't know why.
Because pi double prime of omega.
Well, one thing you can see is that there's only one peak. Well, let me try this on you, okay? This is one thing we thought about, but I don't have proof. If you look here in the normal state, there's just this high frequency peak. Here, all these wiggles are probably due to these finite, these exact annualization stuff. Now, why there's a low frequency peak is probably because once you open a gap in the single particle spectrum, then you can have a collective mode that shows up in the gap. So that would be a cheap explanation of the two peaks.
41 million.
Yes, that would be.
So the resonance, yeah,
That would be the resonance.
is the low energy.
Yeah.
So, just a very nice question, a basic question. How is this computed exactly?
Exact annualization.
With a big board?
Okay, it turns out that the dots here, if I remember correctly, are put at the actual position of the peak. But the shape is definitely broadening. It's 0. The broadening is 0.1.
It's not obvious that the technique is...
Yeah, definitely. If you look here, there are lots of bumps that appear. But as I say, because of what I just said, we sort of trust that these two peaks are real.
The susceptibility is at pi.
If you look, no, the susceptibility is local, so it's integral, it's sum overall. Yeah. But if you divide in Q components, you see that pi is larger than the other ones, but it includes all of them.
But just to play the devil's advocate, if you go back to the previous slide, in the experiment, it looks like the resonance is more like the second peak. Is it the first peak?
No, it should be the first peak, I think.
I thought it was quantum.
Oh, you're right. Yeah.
The resonance is the second.
This is quite dope, actually, 25%.
You don't have highest energy spectrum.
Pardon me?
You managed to have it
Yeah, we have. I can show you all the rest, but they're all. I don't think that they mean anything. This peak here, at the small doping, you see, is around 0.2 in units of hopping. So hopping is, let's say, 400 millivolts. So you get a fifth of this here. So Marcello has papers on this also, and Gould and Minis have a recent one. There's also a recent paper by Sakai and Imada. You understand I don't have time to go through all of these. I barely have time to go through what I want to talk about. But the references are there, and I recommend that you look at them. So what is the origin of pairing when U is large? Okay, when U is large, if you don't put antiferromagnetism, you plot at zero temperature the order parameter as a function of filling. This is half filling. You see that when U is less than the U that's necessary to get the Mott transition, if you don't allow for antiferromagnetism, you will get superconductivity all the way to half filling. But if U is larger than the critical U for the Mott transition, then it goes to 0 before you get to half filling. And if you now scale the order parameter with J, you find that when U is large, the reason it goes down, you see this is U equals 8, 12, 16, 24. If you scale with J, you see they fall in the same region. So the superconducting order parameter scales like J. So we believe J has something to do. Now, what frequencies are important for pairing? Well, the way we decided to look at this is to look at this response function, so this is the Gorkov function that looks how C behaves in time and space. And look at the spectral weight for this function. So if you integrate this spectral weight all the way to infinity, from 0 to infinity, you will get the order parameter. So the equal time, equal space correlation function. Now, if you take this correlation function, equal time, equal space, and you start to move these points L and M away from each other, you will find that it decays with the correlation, the coherence length. So what we are doing here instead is taking nearest neighbor, because it's D wave, and we're sort of looking in time what happens. And it's easier to look in frequency. So we plot what we call the cumulative order parameter as a function of cutoff frequency, or this omega. In BCS, what this does is this. So I plot this function as a function of frequency. In BCS, D wave, it just goes up. When you reach the Debye frequency, it's finished. If you take the calculations for lead, in this paper, 1966, and you do with Eliashberg calculations, there's a gap, a S-wave gap. Then it goes up with, with transverse and longitudinal phonon frequencies, and then it goes down. And the reason it goes down is because of mu star. So in the Eliashberg equations, when you include the Coulomb repulsion, you find that the high frequencies are not binding. So it goes down. So what we find in the case of these cluster calculations is that for large doping, it looks like BCS. It goes up and flat. And in the underdope region, this is the dashed blue curve, it overshoots and comes back, just like it did for the phonons here. So here's a conundrum or a pause that I heard from Doug Scalapino. He said, okay, you're telling me that J is doing the binding, but I know there's Coulomb repulsion, nearest neighbor, so it will kill your effect. In other words, when V is larger than J in mean field, you should not get binding. And this is the argument I showed in mean field theory earlier. If you have charge instead of spin, and you are in the situation of the cuprates where V is 400 millivolt roughly and J is 130 millivolt, you should not get superconductivity. Okay, there are detailed calculations that were done in the weak coupling case by these people, and indeed you find in the weak coupling case that V is detrimental to superconductivity. Ordinary superconductivity, there's the Anderson-Morel phenomenon, where the Coulomb interaction is screened. It extends over a very large frequency range. And if you renormalize it to the Debye frequency, there's this log that will make it smaller and turn it into a mu star that is not too important. But here the log will not be big because the scales are comparable. So the argument cannot work. Okay, so here are the results of the calculations, and we will try to understand why it's like this in a minute. So this is the superconducting order parameter. I just have 5 minutes left at most, as a function of filling. So this is half filling here. If U is less than the critical U for the Mott transition, you see this red curve. This is V equals 0. And this is, again, superconductivity goes all the way to half filling. If I increase V, you see it's rapidly destroyed. By the time V is 1.5, there is nothing left. Now let's take U equals 8. So I'm in the strong coupling, strong correlated case. Again, I look at different values of V, and you see that in the underdope region, it doesn't do anything. I mean, I add V, and it doesn't do much. In the overdope region, it kills superconductivity, the D-wave order parameter, but here not much. In fact, if you look at the largest value of V, it's 3. 3 over 8 is the same as 1.5 over 4. 1.5 over 4 has killed superconductivity. Here, it has not done anything. If you look in the overdope region, The V equals 0 is the red curve. And as I increase V, you see I monotonically decrease the order parameter. That, at large value, remember that at large values of the frequency, we should just recover this order parameter. Now, in the underdope region, it's quite different. There's this crossing. I mean, when V is present, without V, it's the red curve. With V, it's larger at low frequency than it was before. How do we understand this? Well, how do we understand J? Well, J is just second-order perturbation theory. It's just hopping back and forth, and the energy denominator is U when I doubly occupy. In the presence of V, things change a little bit. Because if I have 2 electrons here, in the presence of V, V comes in 7 times here. 1, 2, 3, 4, 5, 6, 7. Suppose that I doubly occupy this site now. V will come 6 times, twice here, and twice there. So the energy denominator now is U minus V. So J is 40 squared U minus V. And this is precisely what you see in these curves. Take the extreme case, U equals 16. So with U equals 16, V equals 0, you see at low frequency, I go to this value of the cumulative order parameter. If I take V equals 8, which is the black curve, you see I go much higher. I go almost twice as high as I did here. And if you look at J here for U equals 16, V equals 0, J is 4 over 16. With V equals 8, it will be 4 over 8. So it will be twice as big. It's about what occurs here. And you see how remarkable it is. We still have superconductivity. J is a quarter here. The J we would have guessed from just U is a quarter. And V is 8, so it's 32 times larger. And still superconductivity survives. It would never do this at weak coupling. Okay, so this section I will skip completely because anyway it's not published and we don't have time. So get back in lecture 3 a little bit too fast. So to summarize, there is retardation. Strongly and weakly correlated superconductivity differ. The penetration depth scales with the number of dope carriers, not with the Luttinger count. It's resilient to V. And the question I did not answer is, does the one-band model capture the key physics? And I guess Henri would answer yes. And I hope I convinced you that at least as a caricature of the reality, it does. And in the workshop next week, I will again look at these questions in more detail and present some 3-band calculations of Giovanni Sordi that explain this. So these are the same collaborators you saw this last time, except Lorenzo has added himself. I did not have time to speak about the work of these 4 gentlemen, and I thank you for your attention.